Welcome back to this machine learning series. In this video, we are covering from where we left off in the last video on linear regression. In our last video, we discussed basics of linear regression and the assumptions behind the linear regression modeling. In this video, we will cover more advanced and interesting topics. We will see how to estimate the parameters from least square estimation method. We will see how to understand the variance of these parameters, the sample variance, how to do hypothesis testing for individual parameter and the group or the sample of parameters in the model. And at the last, we will see the effect of the sample size on the linear regression modeling. So stay tuned and let's get started. Now we want to discuss how to estimate parameters so that you get the best linear regression models. So there are different methods. The most popular one is called the least square method. Our goal is to find the line that minimizes the sum of square distances between our predictions and the actual values. We call this residual sum of square, and it's described by this equation. How do we minimize this equation? Well, in calculus, whenever you have a function like this, you take the derivative and equate the derivative to 0. When you do that, you can solve this equation to get the estimates of the beta, and this is the exact closed form solution of the beta estimates, which is x transpose x inverse x transpose y. If you look at this formula only depends on x. When we estimate our regression coefficients, we are actually performing an orthogonal projection in a higher dimensional space. This projection is represented by this matrix. It's called the projection matrix or the het matrix. This formula is very interesting because it represents the solution that minimizes the square distances between our observations and predictions in this higher dimensional space. And this geometric interpretation really helps to understand why least square works the way it does. Sometimes reality throws us a curveball, and we do get some examples when this matrix is not invertible. And in this situation, the coefficients are not uniquely defined. This happens in many practical situations, such as when two predictors are highly correlated, or when you have more predictors than the number of observations. So these are the estimates, right? The variance of our parameter estimates tells us about the precision of our model. The variance covariance matrix is given by this equation. This formula contains two crucial factors. The first one, x transpose x inverse, this term tells us about the spread and correlation of our predictor variables. The second term, the sigma square, is the inherent noise in our data. The larger sigma square means more uncertainty in everything we estimate. This sigma is the sample variance, and we should not confuse it with the sigma square without the hat, because sigma square without the hat is the true variance. So what is the formula for this sample variance? The sample variance is described by this formula. What it means is that y minus yi hat, this represents how far each prediction was from the actual value. We squared these differences and we sum them up to get a total measure of error. We divide by this number n minus p minus 1 to get an average. And why do we use this number n minus p minus 1? Is because we want our estimator for the sample variance to be unbiased. What does it mean by unbiased? Let's suppose you collect different samples of the data. From this sample, you estimated the variance, you get some point estimate. From the different sample, you calculated the variance, you get a different point estimate. If you take the average from the enough samples of the data, your estimates of the variance should converge to the real variance of the population. Okay, so this is the definition of the unbiased estimator. So now we understand these formulas. Can we really understand the underlying distribution of these parameters? Let's have a look. First, we start with this equation. The noise is the Gaussian noise with zero mean and the variance sigma square. So beta hat follows the normal distribution in which the beta is the mean, which is the true value of the beta, and the x transpose x inverse and the x transpose s inverse sigma square is the variance. The underlying distribution of the sigma hat square is the chi-square distribution with n minus p minus 1 degrees of freedom. We use this distribution to form the hypothesis test and confidence intervals for the parameters. To test the hypothesis that a particular coefficient is 0, we form the standardized coefficient or z-score given by this formula. This follows the t-distribution if we have the finite data sample. Think of the t-statistics like a signal-to-noise ratio. The first term, beta hat, is the signal, how strong the relationship appears to be. The second, the denominator, is the noise, how much uncertainty there is in our measurement. Let's say we are predicting housing price and looking at the effect of square footage. If beta hat is equal to 100, each square foot adds $100 to the price, and our uncertainty is equal to 20, then t is equal to 5. This means that our signal is 5 times stronger than the noise, and that's pretty good. So the bigger this t value, the more confident we are that this variable really matters. This is how you test the significance of including a particular variable. But how about testing the small sample of the variables? Let's assume that you have two models, one model with a less number of parameters and another model with more number of parameters. Then you use something called the F statistics. The formula is given by this. This tells us whether the improvement in fit is large enough to justify the additional complexity of the model. The F statistics asks, is the improvement in prediction worth the added complexity? Are we just making things more complicated without real improvement? High value of F means these new parameters really added some more information. The low value of F means that we are just making things more complicated without any better result. Now we understand the significance test and the hypothesis testing. How do we construct the confidence interval? The confidence interval for individual coefficients are relatively straightforward. We take our estimate plus or minus a multiple of the standard error. So these confidence regions have practical implications for prediction. When we make prediction, we are not just using the point estimate of our parameters. The uncertainty in these estimates contribute to the uncertainty in our predictions. This is why prediction intervals are wider than confidence interval for the mean response. So what is the role of the sample size in our overall discussion? Well, sample size plays a crucial role in all of these calculations. A small sample size, we use t-distribution rather than the normal distribution because it has heavier tails, reflecting the additional uncertainty with smaller samples. As our sample size increases, the t-distribution approaches the normal distribution and our confidence intervals become narrower. The theory also tells us that our estimate becomes more precise with larger sample. We have covered a lot of grounds in this video, from estimating parameters to hypothesis testing and confidence intervals in linear regression. Remember, sample size play a crucial role in linear regression because if you have a small sample, small number of data points, then you need to use t-distribution because the heavier tails of t-distribution takes into account the extra variability due to your small sample. But if you increase the size of your sample, then things change and you can use normal distribution. If you enjoyed this video and learned something new, please give it a like and share it with your friends and family. And please do subscribe to my channel for more videos like these. I will see you in the next video with another topic. Until then, take care. Bye.